just to summarize here, this is what we know already about the membrane potential. When the membrane potential is not at equilibrium, all right, and it's not at -70, right? We know this. At -70, sodium is not at its equilibrium. Potassium is not at its equilibrium. So therefore, the electrochemical force cannot be zero. So there is movement. All right, so when the membrane potential is not at equilibrium for an ion, the electrochemical force cannot be zero. So there's movement. What else do we know? The net force that's going to move an ion across the membrane in the direction that favors it being at equilibrium. What does that mean? The net force is essentially the chemical or the electrochemical driving force, right? The sum of those two forces. And so the force that brings an ion across the membrane, it's going to favor the direction that will help that ion get to equilibrium. So let's go back to this picture here. Sodium is very far from the resting membrane potential, right? And so we have a larger force acting on sodium to get across that membrane. Potassium, however, is very close to the resting membrane potential. And so we have a weaker force on potassium, although the membrane is more permeable. We have a weaker force, okay? And those two phenomena are what bring sodium and potassium to the steady state of balance. Alrighty. And then the last point here was that the strength of the net force increases the further away the membrane potential is from the equilibrium potential. So that just really re-emphasizes what we said. The further away we get from the membrane potential, or the equilibrium potential, the stronger the force, the stronger the magnitude of the force. Okay? So let's look at the examples here. The resting membrane potential is -70 millivolts. Right? The equilibrium potential of potassium is -94 millivolts. So how close, what's the difference here? The difference in the membrane potential is 24 millivolts. So that means that the membrane potential at rest is 24 millivolts less negative than potassium's equilibrium potential. And so what does that mean? It's closer to potassium's equilibrium potential, so the force is going to be weaker. Right? Potassium is not as anxious to get out of the cell. It's not a stronger force to kick potassium out of the cell. But the chemical force out of the cell is higher. Why? We have more potassium channels. Potassium is more leaky. The membrane is more permeable to the movement of potassium. And so what we end up with is a weak flow out of the cell, but a high membrane permeability. A weak flow of potassium out of the cell, but a high membrane permeability. Okay, and this is the opposite for sodium. Let's look at sodium. Sodium is sodium has an equilibrium potential of 60 millivolts. 60 millivolts, whereas the resting membrane potential was -70 millivolts. And so because this is happening in the same direction, we are going to add these two together. So 70 plus 60, that's 130 millivolts. Okay, 130 millivolts. Remember, they're in the same direction. So the electrical force is into the cell. The chemical force is also into the cell. And so we have a strong magnitude of the strength, or of the force, for sodium to flow into the cell, but the membrane's permeability is low for sodium. Right? The membrane's permeability is low for sodium. I really want to drive this point home. The difference in the behavior of these two ions is what gets this neuron to this steady state. The fact that potassium has a weak force, but it has a lot of doors to exit the cell. And the fact that sodium has a stronger force, simply because at rest, the neuron is so much further away from potassium's equilibrium potential. So it has a stronger force. but the membrane is less permeable to sodium, and so sodium has one door, although it really wants to get through that door. Okay. Whereas potassium has many doors, and it really doesn't want to get through those doors as much as sodium. Okay? And so those two phenomena is what brings the neuron to its steady state at negative 70 millivolts, which is a nice, comfortable medium between the equilibrium potential of both of these ions. Okay, but substantially closer to potassium, simply because potassium is more permeable. Any questions so far? Any questions so far? What questions do you guys have? What questions do we have? Okay, so let's continue on here. Now, a neuron at rest, again, just to summarize here, a neuron at rest has a small sodium leak, right? And again, that's a high force, but a low permeability. A high force, it really wants to get into the cell, but it only has one door, so a low permeability. A neuron also at rest has a small or a weak force for potassium to get out of the cell, but a very high permeability. So it has lots of doors, but potassium is not as excited or as anxious. The force is not as strong to kick potassium out. So we have a high force and a low permeability for sodium, and then we have a high permeability and a low force for potassium. And then we have the sodium-potassium pump that is continuously maintaining this environment. So every time sodium leaks in, it's going to kick free sodiums out. Every time potassium leaks out, it's going to pump two potassiums in. So the sodium-potassium pump is helping to keep this environment where sodium can leak into the cell along its gradient, potassium can leak out of the cell along its gradient. This is very important here. So the ATPase pump and these leak channels are crucial in establishing the resting membrane potential.